recording is started, and let me take you to the first item in the practice quiz. Find the angle between these two vectors. Don't look anything up on any of the practice quizzes, just what you can remember.
I can't tell how long I'm going to be able to stay in voice chat.
Okay, the internet's not so good today, huh?
Yep.
Alright, sorry to hear that. You can also, if you've got to jump out, the recording will be up there about, I don't know, an hour or two after class is done.
Okay, thank you.
You're welcome. Okay, let me give 30 seconds more. Alright, so the definition of the dot product is the magnitude of A times the magnitude of B times the cosine of the angle between them. Because of this, the cosine of the angle is the magnitude of the dot product of A and B divided by their product of their magnitudes. So cosine of theta is A dot B, which is positive 2 minus 1 plus 12. And the magnitude of A is the square root of the sum of the squares. 4 plus 1 plus 9. And the other one is the square root of the sum of their squares. 1 plus 1 plus 16. So this is 13 on the top. This is the square root of 14 times the square root of 18 on the bottom. So then theta is the inverse cosine of this. And you can give the angle theta in either mode. When we do calculus in general, like with derivatives and stuff, we have to be careful that we're always in radian mode. But in this case, it's isolated. We could do this fine in degree mode, and it would be 13 divided by the square root of 14 times 18. I'm getting 35.02 degrees. Alright, and give me a little feedback on this first problem. And Cameron, would you like me to read off the problem, or if you're not able to see it?
Thankfully, I'm tracking so far.
You're able to see it? Okay. So then find the scalar projection of B onto A. That's number 2. Very important in this process is the struggle. If something comes up on a practice quiz and you go, oh my God, I can't remember how to do that, you might be tempted to look it up, but it's the struggle that's huge. You want to simulate the kind of things that might happen in a testing environment. And you know, what are the resources? And if you remember some little part, it can be really helpful. And it's raining here at my house now, so if you're getting a little background noise, it's the raindrops. Okay, 30 seconds more. Okay, so if it was me and I was struggling to remember this, I oversimplify the situation. Drawing in 3 space is way difficult. I would draw a simple 2-space model. If I was trying to find this, where the magnitude of A was, let's say, 4, and I'm trying to find the scalar projection of that onto B, and let's say this angle was 30 degrees, and the magnitude of B was, let's say, 9, then how would I find the scalar projection? It would, and I'm starting to remember the notation. Scalar projection, you read it of B onto A. Remember, you have to go backwards. Find the scalar projection of B onto A. Now, when we had done it before, we made a 90-degree angle over here. That would be A onto B. If I did it this way, you project this up. If you're going on to A, you got to be perpendicular to that, even if it goes off it. So that's a 90-degree angle. And then what you're really trying to get is the length of this portion right here. Now this is a triangle right here. It's a right triangle. And if we kind of, look at it again, let's put this 9. Well, you can just say what trig function you want to do. If you do the sine of 30 degrees, so katoa is opposite over the hypotenuse. And the opposite from here is this one over here. So that's not what we want. We want the cosine of 30 degrees, which is the adjacent over the hypotenuse. And the adjacent is the projection of B onto A, this part right here. So that's what we're looking for. Let's call that W for a second. The hypotenuse is 9. And that was not what we were after at all. So then I'm going to say W is equal to, multiply both sides by 9, 9 cosine 30 degrees, and cosine of 30 degrees, that's a known value. I think I remember that. That's the square root of 3 over 2. So then punch this out with my calculator. And I got approximately 7.79. Okay. And that's the same as the scalar projection B onto A. All right. Give me a little feedback on number 2. Can I explain again why you can use either radian or degree and get the same answer? Alright, on the previous problem, if I'd have been using radians, I would have gotten a different answer. It would have been less than 1 radian. That's around half a radian, maybe 0.6 radians or something. So I would have gotten a different answer. But as long as I state what the units are, that's degrees or radians, then I'm okay. Rowan, does that address your question?
Yeah, I understand that you get like a different answer, but like if you convert the radians into degrees or vice versa, you get the same answer. But like usually when we're doing math, isn't that like not the case? Like if you have your calculator in radian mode and you're solving a problem that involves degrees, like you would get the wrong answer, even if you convert it.
Okay.
But
Since this is a inverse trig function, the input to this function is a number. That number is independent of radians or degrees or anything like this. But the inverse cosine is going to be either radian if you're in radian mode or degrees if you're in degree mode. They convert back and forth. All right. Now, the time when you have to make sure that you stay in radians all the time is when you are taking derivatives and using, and solving equations with calculus. That the assumption in calculus with trig functions is always that they're in radians, and they have to be. Calculus doesn't really work unless they're in radians. All right. And then let's go to the next one. Find the vector from the tip of A. I rewrote these A and B again. From the tip of A to the tip of B. 15 seconds more. Okay, suppose I'd forgotten this. How do I do this? I do a 2 space. Suppose I have an A and a B. And I wanted to go from the tip of A to the tip of B. So I draw in the easier space to just remind me of the ideas. And then this, I'm starting to remember, it's either A minus B or B minus A. But always we find the change as our destination or final position minus initial position. And this is, in fact, the change. What makes you change from A to B is this. And so it's going to be B minus A. And so B minus A, well, all I have to do is 1 minus 2, which is negative 1. Negative 1 minus 1, negative 2, 4 minus 3 is 1, and I have it. That's the vector from the tip of A to the tip of B. Give me a little feedback on number 3. Okay, and that's it for the practice quiz today. Questions? Any of the homework or any other questions?
So there was one problem, where was it? On my homework that I think I did right, but like part of my answer didn't agree with the back of the book.
Okay.
It was number 39 and 13.3.
Okay. 39. So calculate the projection of U onto V.
And so like I'd gotten the projection right, but then according to the back of the book, my answer for the scalar was wrong, but I wasn't really sure how I could get the scalar wrong and get the projection right.
Okay. The scalar projection of U onto V is the magnitude of U so it's that one times the cosine of the angle. But the problem is we don't have the angle. So we're going to replace the cosine with the same formula we used when we asked to find the angle, the dot product divided by the magnitudes multiplied together. And when we do that, we get, now this and this will wind up canceling out. So we will get u dot v over the magnitude of v. And u dot v is negative 5 plus 1 plus 10. The magnitude of v is square root of 1 plus 1 plus 4. Which is equal to, on the top you're going to get 6. On the bottom you're going to get square root of 6. And that reduces to square root of 6. So is that what you got, Matt?
The reduce to 6?
It just reduces to square root of 6.
Wait, so why does that, because I got that, why is that reduced to square root 6?
Why does it?
Yeah.
A couple ways. The 6 on the top can be seen as square root of 6 times square root of 6.
Oh.
Okay, and one of them will cancel out. Another way you can do it is think of it like this, where we rationalize the denominator. And then that gives you 6 square root of 6 over 6, and then these cancel.
I see, so yeah.
6.
Would it be incorrect? Would it be incorrect if you, like, would you need to put it into square root 6? Because I had gotten 6 over root 6. I just hadn't turned it into root 6.
You know, if it was a 10-point problem, I might take off 1 point. Because you
Okay.
got it. You just, but another way to see it is you subtract the exponents.
Yeah.
Okay, all these different ways. See it. All right. Any other questions?
I just have a question kind of about the nature of the scalar and the projection, I guess. So the scalar projection, that's just the length of the projection vector.
Correct.
And then the projection is just the projection vector itself.
Correct. And it's, you can think of the projection vector as having two components, the direction and the magnitude. And the direction is the same as u. And then the magnitude is the scalar projection.
Okay, got it. Thank you.
You're welcome. Any other questions? Okay.
Can you actually do 29?
I'm having a little bit of thank you, because I was about to ask.
Boy, Cameron, you're so choppy. I
Something
can hear
somewhere.
about every third word you're saying. Yeah, that's all. Okay. So 29. Let's go to 29. Okay. Find the appropriate measures, approximate measures of the angle of this triangle. So what we have to do is, you're going to do between these two, you're going to find the angle. And that is the same thing as this question problem 1 in the practice quiz. Find the angle between two vectors. And then you're going to do it again between any other pair. And then, after you get the two angles, then you add them up, take 180 minus that sum, and that gives you the third angle. And that's the strategy. Is that enough, Matthew?
Actually, that was me who asked the question.
Rowan?
So you wouldn't try to create two vectors and then use like the dot products?
Oh!
Because that's kind of how I did it.
Yeah, you're totally right. You have to, what I'm assuming, so P, Q, the vector that goes from P to Q is, now it's destination minus initial. So it's 2 minus 0, 2 minus negative 1, which is 3, 1 minus 3, which is negative 2. And then you have Q, R, Q to R. Negative 2 minus 2, which is negative 4. 2 minus 2, which is 0. 4 minus 1, which is 3. And this one is like this. All right. So here we have two vectors. Now the angle between the two vectors, now it's like this problem. Find the angle between those two. Okay. And then you could, after you do that and you have one of the angles, then we can look at like PR. Negative 2, negative 3, 1. Okay, so we could find the angle between these two. And then we could do it again. We could do this one and this one, or these two. Find the angle.
Sorry to interject,
Yes.
but are we sure we have the values for QR correctly?
QR.
Yes.
Alright, so it's destination minus initial minus 4, 2 minus 2,
I think that's correct.
4 minus
Okay.
3. Yeah, that looks correct.
Okay, I'm looking it up. I guess I might have copied it wrong. Yep, I copied it wrong.
Alright.
Wait.
Okay. So Rowan, does that answer your question now?
Yeah, I think I just made a computational error, but I will look back over it.
Okay.
But that makes sense. Thank you.
Okay, and you can check work in, you can try these kind of different operations like in Wolfram Alpha as well. Let me, at least dot product. And we're going to get to cross product too. You probably get that in Wolfram Alpha to kind of check your work when you make computational errors. All right. Anything else?
Sorry to do another check your work thing. I know I've made a arithmetic error already with QR, but do we know if RP is correct?
PR. Okay, let me double check that. -2 minus 0, negative.
Why is it PR not RP? Does it actually not matter?
Either one.
Okay. Never mind.
Because you've got these 3 points in space.
Yes.
And, imagine we're in a 3-space thing. If you had here,
Yes.
here, and then however you're doing this, here, here, there, there, whether I made that error this direction or the other direction, is that going to make a difference in the angles? That's a good question.
Can I?
Yes.
I just decided to say PQR, right? The 3 points.
Okay.
And I decided to find out the angle of this one first. So this one will be RPQ, I guess. RPQ. This one. I'll call it angle A. So that's
Okay.
to find the cosine of
RPQ.
right.
And you could also call that angle P. Some shortcut notation just says that's angle P.
Yeah, to find out the cosine of that angle, then I needed these 2 vectors only. So it depends on which side of which angle that you want to find out first. Since we need to find out only 2 angles, then
Yes. And when you use that formula, it will assume that they are in standard position and that they originate from the point P. So if I did PQ and PR together, then the angle is kind of like you're taking one and then the other, P to Q to R. And if you did it RP like this, then you're going to be getting a different angle. You'd be getting this angle. Yeah. All right. It does make sense. We need to, all right, I had overlooked this. We need to, when you're finding the angle from one point, initiate each of the vectors from that point. So we're really finding angle P here. So instead of the way that I was suggesting to just do it as grabbing them randomly, I would do something like these two, because we initiated both of those at P. And then you'll get angle P by doing that. And then you could use, all right, so if you did QR, or, yeah, then I probably would use something like QR.
QR and QP.
And then I'd initiate it at Q again. QP, get these 2 vectors. And then come up with your other angle from that point Q. That's right. Thank you. Hisu, that really helps. All right. I can see why you were having a question on this, Rowan. I think I was looking at this over simply. The question is actually more complex than I first saw. All right, so are we ready to go on to the cross product now? All right. So we have one way to, quote, multiply vectors, which is the dot product. And this little old dot right here we'll use proper language. It's a dot product, we won't say multiplication, because there's going to be another way to multiply two vectors together. And when we're in the world of scalars, it's a dot and an x mean the same thing. They mean multiply. But in the world of vectors, they don't. This is called the cross product. So we're going to have two ways to multiply vectors. And when we did a vector dot product of vector, we got a scalar. And can anybody tell me real quick, what's the interpretation of this scalar?
Maybe quantity?
It's a number, that's right. And it's a kind of a measure of what?
Like doesn't have direction.
Magnitude.
It's kind of like a magnitude. It doesn't have direction. It's just a scalar. But what does this scalar tell us? What kind of information does it tell us about these two vectors?
It says how much they're in the same direction.
Yes, and it says it in a relative way. It's a relative measure of how much the vectors point in the same direction. Relative to the product of the absolute values of the magnitude, the product of the magnitudes. So that's what the dot product is. The cross product is going to be something very different. It's going to be a vector that we're going to get here. Somebody's still got their mic open. I can hear a little bit of noise.
That was me, sorry.
No problem. Okay, so let's see where this cross product comes from and why we get a vector and what the interpretation of this vector is going to be. It's going to be a way to, quote, multiply vectors that's going to be just as important as a dot product. These two are really two crucial things that you use in physics quite regularly. All right. And to understand this, we need to understand torque. And what is torque? It's a force or movement causing rotation. So we're familiar with this, with bolts and a wrench. And on this wrench, the magnitude of the torque that we can exert depends upon the distance r, and the r will be, see, the magnitude of r is 30 centimeters. Yeah. So r is from here out to here. and its magnitude is 30. So R is this. This is R, and then its magnitude is like this. And of course, if you use a giant wrench, you can get a lot more turning pressure. You use a little tiny, tiny wrench, and oh my gosh, you got to push so hard that you probably can't get a bolt that's kind of stuck at all loose. So it depends upon the distance of R. It also depends upon the scalar component of the force F, but not the force F in the direction that it's given, but in the direction that's perpendicular to R. Because suppose this is, you're inside of a car's engine and you're pushing on your wrench, and the direction you need to push on it is not the optimal direction. You're not pushing exactly perpendicular. It's the perpendicular component of the force that you're pushing with that is going to give you the torque. The other part of this vector, which goes in between these two vectors, is just wasted energy. You're kind of pushing in on the bolt. And that doesn't do anything to rotate it. All right. So notice the contrast of this to dot product. In dot product, let me zip back over here. When we had dot products, and we had an image here, we thought of boosting the speed. And so B is the direction a rocket's going. And A is you're firing some kind of booster rocket to boost your speed. But you didn't fire it in quite the right direction, and so this red component here is wasted energy. That's causing rotation or turning. It turns the rocket. And that's not what we wanted. The only part that counts as boosting the speed is the projection of A upon B. So we wanted the part that was in the right direction. Now we're looking at this part. The perpendicular component is the only part that we want, because now we're trying to find torque. So it's really in contrast. It's kind of the opposite of what we were doing before. Alright. And so when we took before the times the cosine of the angle, because we wanted to get the direction that was the same as this. So we took this times the cosine of it. But now if we'd have taken the sine of that angle, we'd have gotten the perpendicular component. And that's what we're doing over here. The magnitude of F times the sine of theta. All right. Now typically, that's more often seen down here if we'd have dropped this from here to here. So here's the 53-degree angle, and then the cosine is the adjacent, it's the x-coordinate. The sine is the vertical, the y-coordinate, and so you can see magnitude of F times the sine of this angle down in here, that's 53, will give you this green component, which is the same as this dotted line. And note, theta is the smallest possible angle between F and R. And what we mean the smallest possible angle is if you take an R and you take an F, you could make this angle from here to here. You could also make this big angle from here to here. You have two choices. You always take the smallest possible angle. Now, you put these in standard position, so they emanate from the same thing. You're going to get this big angle, but we really want this angle. These two angles will wind up being complementary, and their sines and cosines will work pretty much the same. The only time we really had to pay attention to this was in that triangle problem that we just did, to make sure you got the right angle. Using either one of these, getting sines and cosines will give you the right stuff. Alright, so we'd take it as a 53 degree angle. Alright, so this definition of torque, the magnitude of the torque vector tau, this is something that hopefully makes a little bit of intuitive sense. Magnitude of the torque vector tau is the magnitude of R, longer wrench, more torque you're going to get. The magnitude of force times the sine of theta, which is just going to give you this vertical component of the force if this was horizontal. So we multiply these two together, we're going to get the torque. Hopefully that makes a little bit of intuitive sense. So I have a question and I want you to answer it in your group. So in your group chat, this torque definition has a multiplication symbol in between. Now that's not a dot product because this is a scalar, that's a scalar. It's not vectors. Why are these two things multiplied instead of added? Because a very reasonable assertion might be, all right, the torque, well, yeah, when R is bigger, you're going to get a bigger torque, and when F sine of theta is bigger, you're going to get a bigger torque. Well, that would be true if you were just adding these together as well. So how do we know that they're actually multiplied together and not just added? And if you look at it the right way, and there's probably a number of right ways, but you should be able to explain that. Why it had to be multiplication instead of addition. So think about it on your own for a minute. You can type for whatever possible reason you might want to put that into your group chat, but don't hit enter for a little bit so that everybody can think about this on their own. Okay, go ahead and hit enter. Discuss this in your group chats. Okay, group one, what do you have for this? In your case, it is.
Okay, so I say that, let's say you have R, which is like a positive number, but you have no force, so force is 0. If you were to if you were to multiply those, you'd get 0 torque, which makes sense. But if you were to add them, you would get a positive torque, which doesn't make sense because you're not applying any force.
Ah, nice. Great explanation. If F is 0, the 0 vector, then the magnitude of the torque, is that the way? No. The T was going the opposite direction. The magnitude of the torque vector should be 0. And that only happens with multiplication. And it doesn't happen with addition. Awesome. And let me open the floor. Does anybody else have?
I just said, I'm sorry. I just so simply multiply because it, as Rowan said, it produces work. But addition, it produces a result of displacement, right?
All right, so this, you said it produces work. Work
No, yeah. The work, the force the wrench.
Okay, work is force times distance. And
Mm-hmm.
now the wrench turning isn't really the work being done. The real work that's being done is the bolt is going to screw in to maybe like a piece of wood or something like this. And so the amount of distance the wrench turns actually is irrelevant to the work, but I'm really glad you pointed that out. So this is kind of a nice thing to hold in contrast, where work, if we were computing work done, it would be something having to do with the distance that the bolt goes into, and it would be in a plane perpendicular to the wrench. It's going to move in that, and it would take a lot of force to wind up pushing that thing in, and that's why it goes in very slowly, like this. And anybody else? Any other explanations why it's multiplied instead of added?
I didn't come up with the elegant explanation that Rowe and Jansen proposed, but what I proposed is that there would be a mismatch of units.
Ah, like what? Like what? If you had a units. All right.
And I also said that the lever arm itself is not a force.
Okay. All right. So if we were doing the units, we might be able to see a problem with the units. All right, cool.
We'll also show like force per unit of length, right?
Force per unit of length. Where would that come in?
Well, because you multiply R is 30 centimeters and force is in Newton, so it's whatever Newton meter. If you multiply both, it will give you the torque unit.
Okay. And it'll give you a single unit. All right. Yes. So, all right. And that's kind of back to Cameron's statement of the mismatch of units. The force is some kind of newtons and then multiplying by this. So then you'd be adding these crazy units together. 1 centimeter is another with newtons and such. All right. And let me throw one other possible explanation. And it's a way that I sometimes use when I hadn't really thought of Rowan's thing of 0. But I have had this situation many times in many applied math situations before. And one of the ways I determine whether it's got to be addition or multiplication is if I double 1. If I double either one, double the force, so I push with twice as much energy, I should double the magnitude of tau. Or if I triple either one, double the length of the wrench, I should double the magnitude. Okay, and when you do that, you're going to double, if I had the magnitude of the wrench, suppose this was 30, and suppose the force was 10. Okay, and if I doubled this one, it doubles the result from 30 to 60. But if it was this and I double this, it doesn't double the result. And so that's, I can tell, oh, multiplication's a much better fit than addition. All right. Any questions? Okay. It helps us to get a feel for this. Now, this, we weren't talking about cross product yet, but really this is the cross product. We're going to get into that after we take our break. So let's take a 15-minute break. We will start again at 6:44 p.m. And does anybody need to speak with me individually before I take my break? See you in a bit. get started again. All right, so it totally makes sense that tau is the torque on this, and that the magnitude of the torque is the product, because it depends on, how long our arm is and what force we push with. But what's its direction of tau? Well, the answer is it's in the direction of the axis of rotation. N is defined to be a unit vector that points in the direction in which a right threaded bolt moves using the right-hand rule. So, we're going to wind up we're going to be calling this a cross product in a minute. And we're going to be cross producting, like if we did R cross product F. If we put R first in the cross product, then we would start with our hand at R and move our fingers, curl our fingers towards F, and then the direction that your thumb is pointing is the direction that the bolt would move. That's the right hand rule, and it would move perpendicular to this plane. We go into the other surface. All right, so notice that this seemed to be a definition of tau, but it wasn't really. The torque vector tau is only we were defining its magnitude. If we wanted to define the whole tau, this is the size of it, the length of the vector, but then we need a unit vector in the right direction. And so that's what we have right here. N is the unit vector that's in the right direction, and the direction is, figured out by this right-hand rule. Okay, so F and any two vectors make up a plane. So you have R and F, and you can always put, just like a sheet of paper that'll go through those two vectors. And then you get those two vectors, you have a sheet of paper, it goes through them, perpendicular to that sheet of paper. But there's two possible directions. Use the right-hand rule to pick which direction. That's the direction of N. Unit vector in that direction with this magnitude. All right. Now we've been working on tau and not the cross product, but really this is the setup for the cross product. The cross product. This is directly from the textbook. Definition of the cross product. Given two non-zero vectors, u and v, in 3 space, the cross product u cross v is a vector with this magnitude. So just like we did tau first, we defined the magnitude of tau. So the magnitude of the cross product is this, and the magnitudes of these, it's the same definition that we had for dot product. Let's look at dot product in its definition. Magnitude, but the cosine of the angle theta. But the dot product was not a vector, it was just a scalar, so we didn't need anything beyond this. The only difference is cosines being replaced by sine. Now that's the magnitude of the cross product. And we always take theta to be less than or equal to 180 degrees, between 0 and 180. Make it an angle between u and v. The direction of u cross v is given by the right-hand rule. When you put the vector tail to tail and let your fingers curl from u to v, so the one you start with, u cross v, you put your fingers, the bottom of your pinky finger along u. You curl your hand in the direction, the shortest direction to get to v, and then the thumb. The direction of u cross v is the direction your thumb orthogonal to both u and v. When u cross v is equal to 0, the direction of u cross v is undefined, and it doesn't have a direction. Okay, any questions at this point? All right. Let's go to this theorem. U cross v.
I'm sorry, I have a question. I'm a little confused about the right thumb rule and the picture with the wrench and bolt. So is a thumb goes up, looks obviously like a z-axis. That's the direction of a bolt, correct?
Okay, so if we wanted, you see, because this bolt doesn't look like it's coming out of the screen towards the viewer. It looks like it's going behind the screen. So if we wanted this to be done, we would not, see, because here is R, and the F is here. So if we did R cross F, now if I put my fingers, my baby, did it with my right hand, I would have to have my hand such that, yeah, it would point, R cross F would point just like this picture. I would use the right hand rule and it would point in that direction. Now, thankfully, we're not going to have to really compute this with this right hand rule. We're going to find, just like we did with dot products, we're going to find a huge shortcut for cross products, and it'll compute the answer and it'll give it in the right direction right away, so you don't have to. Although this is the definition of the cross product, it's not the typical way we compute the dot product, the cross product. All right. Hisu, does this make sense that the direction of this would be in the behind the screen?
Yeah, I think I have to keep reading.
Okay.
To understand fully. Yeah. Now
Okay.
confused about the directions and angles.
Okay.
But I'm getting there. Thank you.
All right. So let's come back down here. All right. So theorem. U cross V is perpendicular to both U and to V, because any two vectors is just like if you hold up two pens, maybe you have two pens or a pen and a pencil right now, hold them up in the air and put them, let's say, at a 90-degree angle. You could put a piece of paper so that easily it is in this plane. All right, and now change that angle to, it doesn't have to be 90 degrees anymore, but you can still see that any two vectors can be put in the same plane. And the two vectors define a certain plane. There's only one plane that will do that. And then the u cross v is going to be perpendicular to that plane. All right. So, question. Two questions. What values of theta, for what values of theta is u cross v of maximum length? And for what values of theta is u cross v of minimum length? So, I want you to answer these into your group chat, but don't hit enter yet. Okay, and go ahead and put your answer into your group chat. Hit enter. And group 2, what do you have? What values of theta make this of maximum length?
Why did it in degrees, not radians? And I said 90 degrees and 270 degrees, since that's when sine equals 1. Actually, wait, that's not quite right. It's 90, but it's not 270. It's 90.
Because it's always going to be between 0 and pi, right?
Yeah.
Okay, and then for what value is this of minimum length?
It would be when
0 or 180?
Yeah.
Okay.
Sorry, dude.
And notice that this is exactly the opposite of what we were getting with the dot product. When was the dot product going to be maximum? When was it going to be minimum? The dot product was maximum when u and v are pointing in the same direction. But here, 0 degrees is when they're pointing in the same direction. That's when you're going to get the minimum. But remember, what you're getting here now is the amount of turn, rotation, or if you kept the same model from before, a booster rocket, we're trying to turn now, and we're not trying to boost any speed. And so you would say, oh, well, how much turn did you get when you fired it perpendicular? When you fired it in the same direction as you were going? Well, you didn't get any turn at all. Okay. And theorem. U and V are parallel if and only if. And by the way, whenever you see if and only if, it means that this implies this, and that this implies that. So that's why we put double arrows for if and only if. And if two things have this if and only if relationship, then mathematically we think of them as equivalent. U and V are parallel if and only if U cross V is equal to, well, this number from what
0.
Yes, it's got to be 0. If U cross V is 0, then they had to be parallel, either going in the same direction or exactly opposite directions, 180 degrees apart. And then there's no turning that happens, and so there's no actual vector. It's a 0 vector, and so there's no direction to that cross product. Alright, and then, alright, these exercises, you're going to have to think about the right-hand rule to get these correct. So, I cross J, and go ahead and do the I cross J and think of what you're going to get on that. I'll give you a quick 30 seconds. Okay, somebody's got their their mic not muted, getting a little bit of noise. Okay, so here is I, if it went 1 unit. Here is J. And we're going to use the right-hand rule. And I cross J, you got to put your hand, you got to distort it. So like it's thumb pointed up, coming out of your computer directly towards you. So the bottom line of your little finger is along the I, and then we curl it towards the J, and then we can see that this is K. The result goes up here. Because this was a magnitude 1, this is a magnitude 1, so we know this has got to be a magnitude 1, and we know the direction had to be straight up. Any questions on how we got K? Alright, if there's no questions on that, do the other 3. And when you get your answers, put them into your group chat, but don't hit enter yet. Okay, go ahead and hit enter. And group 1, what are you getting for these?
Let's see, we've got a bit of a spectrum here.
So give me multiple answers.
Okay, so for the first one, we've got K and negative K. For the second one, we've also got K and negative K. For the third one, we've got I and negative I. And then for the fourth one, we agreed on positive J.
Okay, well, let's look at this second one. J cross I. Alright, so if I kept my hand so that I put it right on top of my right hand on top of my computer monitor, so that my little finger was going along the direction of J, then to curl it forwards, I would not be going the shortest path to I. I'd have to go 720 degrees to get to I. So I have to flip my hand upside down, so the thumb is pointing down, have my little finger going along J, and then J curling my fingers to I, that's the short path, the 90-degree path. And then I point straight down, so this is the minus 1 over here. So that one is the minus, right here. And then the J cross K, J and K. So I'm going to put my hand up, my right hand is resting on the monitor, and my thumb is pointing directly towards my face. And then I curl up towards K, and then my hand points in the x-axis. So J cross K, not K here, but I. And it's positive I, right there. And then the bottom one, I cross K. So I have to put my bottom of my hand, the little finger, on I. But if I have my thumb up, now I'd have to rotate it so that the thumb is pointing in the negative direction of the y-axis. And then I could curl straight up to K. So this is going to be I cross K. This is going to be negative J. If I had it the other way, I would be curling underneath the y-axis, or the xy plane, to come all the way around. It would be way inefficient. Alright, let's go to Discord, and everybody tell me how they're doing with this right-hand rule with this C. Are you mostly confused? Pretty much got it? Where are you at on that? Let me see. Most people are confused. And this would be way easier to teach if I had, if we were in person. Let me try one thing with my camera. Alright, so here's the camera, and if I had let me just see if it works. Alright. X, Y, Z, right there. So if I'm on the Y, and I curl, so if I had Y cross, or I, the Y cross the Z, it's really the J cross the K. I'd have my hand here, I could curl up to there, and my thumb would point in the direction of the x-axis. And alright, but once again though, if you don't get the right hand rule, you'll rarely have difficulties, because almost all the time. There'll be a few exceptions, but very rare. Most of the time, we're going to be getting the cross product in a way we don't have to think of the right hand rule. We'll use this big time shortcut and it'll give us the whole thing. Alright, but if you're still confused on this, I think you'll just have to kind of reread the textbook. And there might be some videos that show it better too. Alright, let's go from here to I'm going to skip that one to make sure that we have enough time for the good stuff. Here. Alright, number 5. Here's the vector A, the vector B. What is A cross B? Cross product. All right. We would have a massively hard time figuring out A cross B right now, because we would probably try to do this with the definition. We'd probably go, oh, it's the magnitude of A times the magnitude of B times the sine of the angle. But remember, the result of this is a vector. So then we have to put that in front of a unit vector that's in the right direction. Now, the magnitude of A is no problem. Magnitude of B, no problem. Sine of theta would take me a while. I might have to remember the angle between these two. You could figure it out. That was the practice quiz problem number 1 today, with dot products. And you could, take a while to figure out what theta is by the inverse cosine. And then you take the sine of that, and we could get that. But then this n, we wouldn't be able to get. It's in a direction that's perpendicular to the plane that makes up both of these vectors. How do I get that? So, although this question sounds like, oh, easy question, what's A cross B? By this definition, we're just paralyzed. We just can't do this. Answer, at this point, we can't answer this. We could not get in at this point. Thankfully, there's a mammoth shortcut. Just like there's a mammoth shortcut to find A dot B, there's an easy way to find A cross B. It's a lot more complicated than A dot B, but it's quite a huge shortcut. In order to do this, first we need a review of determinants. And determinants of matrices, determinants of 2x2s and 3x3 matrices. And let's go over to Discord. Some of you may have never had determinants of matrices. If you had determinants of matrices, tell me a little bit. Yes, I've had it. And then the state of where you're at. Maybe I had it and I've totally forgotten it. Never had it at all. Never had to, go ahead and let me know what you know about matrices and determinants. Okay, so we're going to start at ground zero. On determinants. When you have a matrix, like the matrix A, we put brackets around it. When we put the determinant of A, now A is not, I'm kind of using a vector notation. When we use, say, the determinant of A, we'll put solid bars around it. The determinant of A gives us a single number. And here, if I multiply these two together, so on a 2x2 matrix, it's this minus this product. So it will be 1 times negative 1, always subtract, and then these two multiplied together. Okay, and so what you get is a number for the determinant of a matrix. This number tells you something really important. Usually we use matrices in systems of equations. It might have been like this system, equals some number and equals some other number. And then this number is an important property of this system of equations. Now, let me just have you practice that real quick. Take the determinant. Of that matrix. It is 15 minus 2, which is 13. Determinant of a 2 by 2. Any questions? All right, now let's expand 3 by 3 matrices. The determinant of a 3 by 3 matrix
is more nuanced.
Yes. All right. What you do is you choose a row or a column to move along, and then you can figure it out. And then we're going to choose, let's say we're going to choose this top row to move along. Now if I move along this top row, you pick the first element in the row, 1 times the 2 by 2 matrix that will result from eliminating the row and column of this element that you just picked. So I use the 1 and I eliminate its column and its row, and I'm left with this 2 by 2. Then the signs alternate. So this one, the next sign is minus, and then the next sign after that will be plus. And then I go to the next item in the row, and I get the determinant of the 2 by 2 matrix that results from eliminating this column and this row. And then it's 0, 1, negative 1, 2. And then I go to the next item and I go plus 2 times the 2 by 2 that results from eliminating its column and its row. And now you know how to do determinants of 2 by 2s. So let me give you a quick minute to get ahead of me. Get all the way down to the result, and then I'll do it and you can see if you got it right. So this was minus a negative, and this was minus a negative. And negative 2 and 4 is 2. So the determinant of this 3 by 3 right here turned out to be 2. Right. And the theory goes that you could pick any row or any column to follow along, but for all that we know, for all that we need, we just need to know how to go across the top row. Okay. Let me give you one more. Determinant of a 3 by 3 to make sure you have the idea. And take the determinant. Of that. And remember to move across this top row the same way that we had done. And I'll give you a minute to get ahead of me, and then you can see if you did it right. Okay, so this is 2 times the determinant of the 2 by 2 that results from knocking out its column and row. Minus -1 and delete its column and row. Now this last one I'm not even going to bother to fill in, because 0 times anything is 0. And this becomes 12 minus 2. And that's 10 times 2 is 20, plus 5, 25. Okay, come over to Discord, tell me if you're okay with this, how you feel with getting a determinant of a 3 by 3. Can you follow the pattern? Could you repeat this now? Is that enough? Okay, alright, good. Let's come back over here. So, the way that we do the cross product, the shortcut. If we're evaluating the cross product of U cross V. Now, this is U written in terms of components I, J, and K, same with V. And notice, you put, and this is not really a valid determinant, because you can't mix up vectors. I, J, and K are vectors. And scalars inside a determinant. You couldn't make a matrix out of this. It's just a way of, it's a shortcut way of visualizing and working with it that works out really nice. So if you could make a matrix like this, we just imagine that we can, we put I, J, and K across the top row. And then whatever are the components of this vector, they go next. And the second vector goes down to the bottom. And then, normally we'd put the I up front, but it gets put back here. So you have, and then you eliminate its row and column, and you're left with these 4. That goes here. And then minus, and then normally the J would be up front, but we just turned it around here. And you've eliminated this row and this column. You get U1, U3, and so on, like this. So this is the way, the shortcut way, that we evaluate cross products. So let's do it. So let's take U example. Two, 3, -9. B is -1, 1, -1. And find U cross V. Well, that's easy. We make a determinant of a 3 by 3. We put I, J, the unit vectors in each of the 3 primary directions across the top row. We take the elements of U next, and then the elements of V. And then we do just what we've done before. Take I times the 2 by 2 that's left over. And when I cross out this row and this column, minus J, always alternates in sign. Delete its row and column. Plus and then I get I, and that's -3 plus 9, -2 minus 9, 2 plus 3, and I get that is my 3-space vector that is perpendicular to both of these vectors.
It should be positive 11, J.
This,
Yeah.
oh yes, negative and negative makes plus. Thank you. All right. Any questions? So this is just a computational detail, how we quickly compute the cross product of 2 vectors. And let's go down to the geometry of the cross product. So let U and V be 2 non-zero vectors in 3 space. And we already had this before for part 1. The vectors U and V are parallel if and only if their cross product is 0. So it's kind of like the torque. What amount of torque would you exert on V if they're parallel? None at all. So you get 0. Number 2, if U and V are 2 sides of a parallelogram, then the area of the parallelogram is this. So it actually gives us, so let's see this if we were doing it in two space. It's much easier to visualize in two space. U and V. But the same principles hold in a higher space. Well, in three space for the parallelogram. Alright, so this, if you project straight down from V to V onto U, this length, remember, is magnitude of V times the cosine of the angle theta. And this is the magnitude of V the length of the side is the magnitude of V times the sine of theta. Alright, so what we're going to do is if I multiplied this length, which is magnitude of U, times this, I'm going to get a rectangle. And the rectangle would be the length of this, bring it over, would wind up being, I have this little bit of distance, I got to bring that over here. I would get the area of this rectangle, multiplying this length times this length to get this. So it's the area of this blue box that is the cross product. But the area of that blue box is exactly the same as the area of this parallelogram. You can see that by this area right here. If you cut that out, moved it over to here, you get the parallelogram. So this is a real simple visualization. It's an important formula to memorize. If you go into cross products in more detail, you'll want to have this visualization. You'll want to remember this. It's the area of the parallelogram when you take the cross product, and then you take the magnitude of that cross product. Any questions there? Okay. Then, what we've done in all of calculus, starting from calculus 1, when we first learned limits, we learned, all right, when we learned something new, what are the properties of limits? Then we learned derivatives, and what are the properties of derivatives, and so on. We finally have dot products and cross products, and we learn what are the properties of these things. Now, dot product was commutative. If you did u dot v, it got the same result as v dot u. But the cross product is not. If you change the order in the cross product, you get them to point in opposite directions. So it's negative. Constants times them, they just come out. And then cross producting, distributing it into a sum, kind of works nice like regular multiplication does. Right, so it's some distributive properties. Alright, and here, some of these expressions make sense, and some of these do not. They're impossible things to do. So, we'll go through them one at a time. Let's start with A. A dot B cross C. Is this meaningful or is it nonsense? And so one at a time, go into your group chat and then type in, you could say, yes, it's meaningful, or no, this makes no sense, you can't do this. For A, let me give you 30 seconds to think about it, so type it in but don't hit enter yet. Go ahead and hit enter on A. And group 2, is this meaningful?
I said that that does work since the cross product of B and C will become a vector, and so then you can just multiply or do the dot product of those two vectors,
So this is meaningful.
and it's a scalar.
It's meaningful and it's a scalar. Great. Meaningful scalar. Okay, do part B. Same thing. State this to your group chat, but don't hit enter yet. Go ahead and hit enter. Group 1, is this meaningful?
Well, it's not meaningful because you can't take the cross product of a vector and a scalar, but like you could multiply a vector by a scalar. So, but I guess we're viewing the x as a cross product, right?
Yes, this does mean the cross product if it has a vector and then that. So this makes no sense. And if you had to make sense of it, you would do exactly what you did. Say, all right, we'll call this multiplication of a scalar times a vector. Okay. And C. Go ahead and hit enter. Group 2. Does this make sense?
I said yes since the cross product of B and C becomes a vector, and so then if you do the cross product of A and that other vector, you'll still have a vector.
Meaningful. And we get a vector. Now the vector that you get, what is its properties? One thing I can say about it is this new vector is going to be perpendicular to A. Is this vector going to be perpendicular to B? That I'm not so sure. It's perpendicular to this vector is perpendicular, this vector in parentheses is perpendicular to B and C, but then this other vector is perpendicular to that vector, but at least I know that it's a vector that's perpendicular to A. Alright, let's go to D. Hit enter. Group 1. What is this?
We said no because again, it's going to be a scalar times a vector, and you can't cross product those. Yeah, you can't cross product a scalar and a vector.
Okay, E. Go ahead and do that. And F. Do the last two. Go ahead and hit enter. Group 2, what about E?
That does not work since we'll be taking the cross product of two scalars.
That also is true there. And what about this last one? Group 2 again.
That would work since both of those individual parts will become vectors and you take the dot product of the two vectors.
Makes sense. And the result is what? Scalar or vector?
A scalar.
Okay. And that takes us to the end here. So the homework is 13.4. Reminder. So on graded homework, if I mark something wrong, you can upload into the same file that you uploaded the homework in. You only need to upload the part that you corrected. I already gave you credit for everything else, so I don't need to see the whole thing again. So if it's just like one problem you did wrong, just replace that upload with that one problem corrected, and then you have a week to do that after I correct, and then you can get 7 out of 7 on each one of these assignments if you just keep at it. If your correction though is incorrect, I'll tell you, and then you have to redo it again. So, all right. Any questions before we stop for the evening? All right. Today is Wednesday, so have a good weekend. I'll see you all next week.
Okay, thank you.
Thank you.